So, coming at you with the next video installment during the coronavirus pandemic. Hard Science is still here for you, making sure you learn even when you're at home. All right, so today, notes are on Hard Science. It's all pretty and colorified for you. All right, so if you want that, it's got some definitions, some comparison charts, some pros, cons, a little more detail than what we got. We're going to kind of hit most of it. So here we're talking about nuclear fission versus nuclear fusion. All right, so pretty crazy looking, right? Something else over there. But so what happens? So we talked about protons, neutrons, electrons. We talked about ions, isotopes, and all that kind of stuff. But now, a little bit more into this nuclear chemistry. So we're only focused on the nucleus. The nucleus is the center part of the atom that has protons and neutrons in here. So we're not going to talk anything about any electrons. You're not going to see electrons drawn around the atoms. We're only focused on the nucleus, the nuclear chemistry of this. And there's two reactions we're going to talk about specifically today: nuclear fission, nuclear fusion. This is not just a bunch of scribbles. It's a real thing. They call it nuclear fusion. Oh, I'm wrong. Nuclear fission. Sorry. I just like nuclear fusion better, but this is nuclear fission. So, what is going on? All right. So, it all starts with we have a large, unstable nucleus. Okay. This nucleus, the reason why it's unstable is because it's so big. And if you don't remember, there's 92 protons in there. That's 92 positive charges inside of that nucleus. What do positive charges do? They repel. So how are we going to hold them together? Well, it's just very strong, the strongest force known to man, the strong nuclear force. It holds protons together, but although it's the strongest force known to man, it has the smallest range. So kind of to help you imagine, this is my area of effect for my strong nuclear force. Anything that was kind of in there, it's good. It'll hold it. It's not coming out. Life is good. It's stable. But as these atoms start to get big, they kind of exceed the range of the strong nuclear force. They're unstable. All right. What do you know about somebody being unstable? You can just kind of give them a little tap, and they're going to fall over, right? Or somebody who's not, who is very stable, you kind of give them a shove, they don't really move. This one's unstable. So if we were to take this neutron, one, high atomic mass of 1 with 0 protons. If it has a mass with no protons, or if it has a mass and it ain't a proton, it must be a neutron. Also, N stands for neutron. Anyway, if you take this neutron and you shoot it at an unstable atom, right? Walk up to your buddy sitting on the porch. He's unstable. You just kind of give him a little shove. He's going to fall off the porch, right? Well, if we take this neutron and we slam it into this unstable atom, nuclear fission will occur, right? What that means, nuclear fission, is it's going to split that atom, right? Right? Going to split that thing. Right? When it does, this is a heavy, unstable nucleus. It's going to create two lighter, more stable versions. Right? So this has a mass of 235 with 92 protons. This version here has a mass of 141 with 56 protons. And this krypton up here has a mass of 92 with 36 protons. So it split it right down the middle. Well, not really down the middle, but it did split it into smaller stuff. So if you remember, which you probably don't, this happened, right? So if I separate this, the total mass on this side must be equal to the total mass on that side. This is that law of conservation of mass thing I've been talking about a little bit here and there. So if we look at this, 1 plus 235, we have a total mass of 236 on this side. Right? If we add these two pieces, okay, 141, 92, I should be able to do that in my head, but I'm just going to do this to make sure I'm right. We have a mass of 233 over here. So we're lacking a little bit of mass, right? So something else must have happened because mass cannot be created or destroyed. It can only change form. So there must be some more mass over here somewhere. That's what these are. So it splits this big unstable atom into two pieces, two fragments, two daughter nuclei, right? But it also releases free neutrons, right? So mass 1, 0 protons, it must be a neutron. It releases these 3 neutrons. So if we add them to the mix, there's 1, 2, 3. Okay. So although we're splitting up, changing, cracking things open, all that kind of stuff, there's the same amount of mass after the fission as there is before the fission, and that complies with the law of conservation of matter, or mass, whatever it is, one of those two. So that is nuclear fission. Now, nuclear fission, we currently can control it with our technology for the most part. So this is what, in nuclear power plants, we use nuclear fission. What we do is we set off a nuclear fission reactor in these reactors, right? And it releases a whole bunch of heat. And that heat heats up water. The water turns to steam. Steam flows through the pipes, turns the turbine turns the generator, and we know when we turn the generator, we get electricity. All power production is pretty much based on turning that turbine so that we can turn that generator. Here we use the heat from the fission to do so. This is great, right? It's a chemical reaction that releases heat. There's no gas emitted, right? There's no greenhouse gases emitted, should I say. It's not going to increase the global warming. It's not going to pollute the air. It's not going to pollute the air you breathe. It's not going to make the earth hotter. There's really a lot of things good about it versus burning fossil fuels. Where fossil fuels, you see the smoke coming out in smokestacks. We're releasing greenhouse gases. We're heating up the climate of the earth, which is not good. It's not. I promise you it's not. Because I'm pretty sure it's not good. Right. But nuclear fission is not all great. Okay. So yes, fossil fuels is releasing, greenhouse gases into the earth. So when I say fossil fuels, I'm talking about burning coal, burning methane, natural gas, doing these kind of things is polluting the air. But it's not creating any radioactive waste. If you know about Chernobyl and stuff like that, if the nuclear power plant melts down, humans will not be able to live in that area for however many miles is affected forever, pretty much, like 240,000 years, right? So fossil fuels ain't gonna kill us now. Eventually, it might make the humans' race go extinct, but nuclear reactions, although risk level is very low, are dangerous for nuclear waste. And there's a lot of problems that go on with that as far as storing it. I mean, how you gonna store something? Can you store your garbage for 240,000 years? Make sure nobody touches it. Make sure it don't get wet. No, man, that's hard to do. It's expensive, but it does kind of solve climate change for now. But also we use nuclear fission for like nuclear warheads. Those are kind of scary. But anyway, our nuclear submarines, aircraft carriers, research, particle accelerators, stuff like that. But there's something on the future, the event horizon, that hopefully we'll be able to harness. Nuclear fusion. Nuclear fusion is a reaction that drives the sun. The sun. Pretty cool stuff, right? So we got to be able to take the sun and put it in a bottle. It's going to be hard to do. But I do think one day we'll get there. We're doing cold fusion reactions right now. We're working on it. We're trying to work in that way. The reason why this is so important is because it's the clean energy that solves all the world's energy crisis. It releases more energy than nuclear fission found. If you had like a gallon of hydrogens, that's enough to power New York City for 3 days. It has nothing bad. There's no radioactive waste. There's no pollution. There's no nothing. Right? We got to figure it out. So now that's our next discussion. Put a lot of effort in that drawing. It's just gone like that. You know what I mean? So what we're going to do with nuclear fusion, we're going to take 2 small light atoms. This is what happens in the sun. This is how all elements are formed that we know about. This is why we are star stuff, right? So we'll take, we'll take a hydrogen 2 isotope. We'll take a hydrogen 3 isotope. And it's got to be like sunlight conditions. You know what I'm saying? Like, it's got to be super hot. It's got to be super pressure. It's got to be super dense. It's got to be things flying so fast that they don't repel. And we know positives repel each other. But if the conditions are right, like the sun, these things are going to slam each other. It's going to break that strong nuclear force and reform it, releasing all kinds of energy. When it does that, it's like bang, right? It's going to release, right? Proton plus proton, 2 protons. And it's going to have 2 of these neutrons with it, right? It's going to release what has 2 protons? Helium. Right? Mass is 4, protons is 2. Now there's still that other, remember, law of conservation of mass, we've got 2 protons, 2 protons. 3 neutrons, we need 3 neutrons over there. So that is the byproduct of nuclear fusion. We're just going to create helium. Guess what? We're running low on helium right now. Your favorite balloons at the Ingalls supermarket you like to blow up and float through the air for people's birthday parties, eventually, we ain't going to have no helium for that. But if we figure this out, not only do we save the world's energy crisis, we figured out the solution. You can blow your balloons up with helium too, because that is the results. That's the pollution from this. It's not even pollution though, right? And then these neutrons, just like in fission, when those free neutrons come out, they're going to go hit other atoms, or they're going to combine with other atoms. They're going to keep the reaction going. This is called a chain reaction. So that's kind of the rundown of it, of everything, fission and fusion. Hope this helps. Remember, fission's arguably better than fossil fuels. It kind of solves the global warming problem, keeps us from leaving too big of a carbon footprint. But fusion, we got to get to fusion. We got to get the technology to control fusion. Maybe one of y'all will figure it out.